Welcome to the tutorial on numerical on state machine notations. As a first numerical, we have a sequential circuit which is having one input and one output. The state diagram is given here and we need to design the circuit using the JK flip-flop. So looking at the state diagram, the first step to the solution would be to identify the number of states that are involved. So we can see that there are 4 states that are involved and they are 0, 0, 0, 1, 1, 0 and 1, 1. And because we have 4 states, we will be having 2 variables, QA and QB. If you observe the transition arc, you can see that there is one input and one output. So I'm going to name the input as X, which can either be a 0 or a 1, and one output as Y, because that is what is being specified in the question. Even this output can be either 0 or 1. So the next step in the process would be to draw the application table for the JK flip-flop. That is because they have asked in the question clearly that we need to design the circuit using the JK flip-flop. So we need to know the application table for the JK flip-flop. So here we have represented the present state as QT and the next state as QT plus 1. So for the various combinations of the present state and the next state, the application table for JK is of this form, and how this application table is generated you should be aware about. So kindly refer to that tutorial and you will be able to understand better. Usually this application table would be generated from the next state table. So from this application table we go to the transition table. So in the transition table we have already identified that we are having 2 variables, QA and QB. So the present state will be now termed as QA and QB, having 4 combinations. That is because you can see that 4 states were involved, so 0, 0, 0, 1, 1, 0, 1, 1. And the next state would be represented as QA plus and QB plus, QA plus and QB plus. As mentioned earlier, output is a single output Y. Input is X. So this input X can either be 0 or it can be either 1. So that is why we are having a total of 2 columns when X is equal to 0 and when X is equal to 1. Now what we need to do is, for this particular transition table, we need to look into the state diagram and fill these parameters for the next state X bar Y. So if you see the state diagram, you are at 0, 0. And the input is 0, output will be 0, and you are going to have a transition to 0, 0. You are at 0, 0, input X is 0, Q plus will be 0, 0, output is 0. Let me take another example. Say you are at 0, 1. You are at 0, 1 and the input is 0, output is 0, you make a transition to 1, 1. So from 0, 1, the next state would be 1, 1 and the output is 0. So this way you will be able to fill all the parameters or the contents of this next state corresponding to X is equal to 0 and X is equal to 1. In the state diagram, the left hand side will always correspond to X and the right hand side will correspond to Y. So X is equal to 1 means it is this, Y is equal to 0 means it is on the right. Whereas here X is 0, Y is equal to 1. Once you know the transition table. From the transition table you obtain the excitation table for the JK flip-flop. Now here the present states are two, QA and QB. For the excitation table, you are going to replace Q with the flip-flop. So QA and QB is present. So QA and QB, QA will be replaced with JA and KA. QB next state will be replaced with JB and KB. So here, if you see, you had QA to be equal to 0. Zero, 0. 0, 0 is 0 bar. So 0, 0, 0, 0 is 0 bar. 0, 1 is 1 dash. 0, 1 is 1 dash. Next is 1, 1. If you look at the application table, is dash 0. So 1, 1 is dash 0 here. So in a similar manner, you have to compare the QA and QA plus of the transition table to fill in the contents of the excitation table for JA, KA. Similarly, if you want to fill in the contents of JB, KB, you have to compare QB of the present state and QB plus. Only then it is possible for you to fill in the contents of this particular JB, KB. Y will remain the same as that of the transition. Similarly here Y will remain same as that of the transition table. Once this contents are filled, you are going to write the expressions for JA, KA, JB, KB, and this way you can obtain the shorthand decimal notation, simplify the Karnaugh map for JA, KA, JB, KB, and for the output variable Y. So coming back to this, here if you observe, JA was corresponding to the zero, zero, 0, 0, 1, 0, 1, 0 combination. So 0, 1, 0 is nothing but 2. When you write JA, it is QA, QB, X. QA to be the MSB, X to be the LSB. Similarly, you need to write for all the parameters here, and KA has to be combined here as well, JB, KB, and Y. So once you write all the shorthand decimal notations, use the Karnaugh map and obtain the expression, simplified expression. So JA is obtained as QB XORed with X, K is obtained as QB XORed with X, JB is QA into X, KB is QA plus X, Y is equal to this particular expression. Once all these simplified expressions are obtained, it is easy by writing all the simplified expressions. That is, these expressions will be called as the excitation equations because they are the ones generated from the excitation table. Now you will come to know as to how many flip-flops you need to use, that is how many JK flip-flops you need to use, and how you will get the output expression Y to be. So because you have JA, KA, JB, two JK flip-flops, you need to make use of XOR operation and OR operation to obtain the variable Y. So this is one quick numerical which comes under the state machine notations. So they can give you any state diagram and they can ask you to design the circuit using any type of flip-flop. Not necessarily it should be a JK flip-flop. How to identify how many variables are required is clearly based on the number of states that are required. So looking at the states, you can identify how many variables would be required. So you can see that since these 4 states have to be represented using 2 variables, so that is why 2 variables QA and QB are used. So moving on to the next question, you have these 2 questions which are exactly the same. So I am considering them to be an exercise numerical which you will be able to solve very quickly. So a sequential circuit has 1 input and 1 output. The state diagram is shown below. Design the sequential circuit using D flip-flop. Now in this particular case, they have specified the states, okay? 0, 0, 0, 1, 1, 0. Since you have 0, 0, 0, 1, 1, 0, this is clearly need to be represented using 2 variables. So you will require QA and QB. So that means you will require 2 D flip-flops for the design. And if you compare this particular exercise 1 with the one which is shown in exercise 2, these 2 numericals are exactly the same. In this case, this is represented using the binary representation, whereas here it is represented using the variables. So the left hand side corresponds to the input, the right hand side corresponds to the output. And if I was to consider, I can consider the output to be either represented as Y or to be represented as Z. Anything as I wish. So in this particular numerical, they have represented the variable as Z and input is represented as X. Rest all the parameters remain the same. S1, S2, S3, if I have to consider them in order, it would be 0, 0, 0, 1, 1, 0. Then if you compare the arcs or the transitions, you would observe that all complemented terms correspond to logic 0 and uncomplemented terms correspond to logic 1. So this numerical is exactly the same, just that the representation is different in these 2 cases. So if this numerical has to be solved, you need to just solve in a similar manner like the one which we have solved earlier. Try to represent in terms of zeros and ones and it would be very much simpler. So all you need to do here is, if the question is asked in this particular form, just try to represent the equivalent of this in this particular form and you can solve it very, very easily. Moving on to the second type or the variation of the numerical. Here the question says you need to construct the state table for the following state diagrams. There are 2 state diagrams that they are given and we need to construct the state table separately for these 2 diagrams. So let us deal with them individually. So I am looking into the solution for the first one. So here I am representing the left hand side to be the input, which is X, and the right hand side to be the output, Z. So since these states have already been specified in terms of variables, clearly I know that there are 3 number of states. So present state is A, B, C, and the next state X bar Z will have the form 0 or 1 and output variable will be Y. Input is 1, output is 1. So A to A transition, input is 0, output is 1. A to B transition, input is 1, output is 0. You are in B present state and input is 0, that is here, and you move to C with an output 1. You are in B, input is 1, and you move to state A with an output 0. You are in C, you move to A with an input 0 and output 0. So A 0. You are in C, you've moved to itself with an output 1. So this is how we obtain the next state table for a given state diagram. So this is the state table for the first circuit. Moving on to the second numerical. So here this particular representation is for the Moore machine, and in this particular case they have specified you a total of 4 states A, B, C, D. X is the input, Z let it be the output. So if you observe here, they have specified you what will be the output within the state. So you are moving A to A with an output 0. This arc will always contain the input, okay? A to A with an output 0, A to C when the input is 1 and output is 0. You are in B, you move to B with an input 0 and output is 0. You are in B and you move to A, the output is 0, input is 1. You are in C, you move to D with an input 0 and output 1. You are in C and you move to C itself with input 1 and output 1. So this always corresponds to the output in the Moore machine. So you should remember that. That is why we get the state table in this particular form. You are in D, you move to B with an input 0 and output 0. You are in D and you move to D itself with an input 1 but output is 0. So similarly, you can solve a lot of numericals using the state machine notations, wherein they provide you the state diagram and you have to design the sequential circuit.